So in this question, it should have been under chemical periodicity, but does not matter because we can predict the change in ionic radius based on what you have learned from atomic structure anyway. So these are third period elements. So they will come under general periodicity trend again. So from sodium all the way to chlorine, we can say they want to talk about ionic radius. So in terms of the atoms, their number of proton increases, their number of electrons increases, okay? But we are talking about the same n equal to 3 shell. So your shielding is roughly constant. Therefore, your atomic radius generally or consistently gets smaller because your atomic radius, because your effective nuclear charge gets higher across the series. So this is the trend for atomic radius. Okay, the ionic radius, however, will look somewhere like this and then like that. So the anions are bigger than the atom, the cations are smaller than the atoms. Okay, so when you think about it, the cations, so such as Na, Mg, and aluminium. So when you have the cations, they're gonna look like that, and then you can also think about the number of protons and the number of electrons: 11, 12, 13, 10, 10, and 10. So you have the same number of electrons, but your number of protons continuously increase, so your nuclear charge increase. Obviously your size is going to decrease because your Z effective will be higher. And then importantly, when you consider the anions, you can go the other way, but I'm going to consider Na versus Na plus. When you look at the protons and the electrons, same number of protons, the atom has the same number of protons and electrons, but the cation has only 10 electrons there. So that is 1s2, 2s2, 2p6, 3, no, it stopped at 2p6. So it's a maximum 2 shells being occupied, whereas there, I hope you can see it is actually a group 1 electronic configuration there, because you haven't lost the electrons in the n equal to 3 yet. So it's 3 shells that are filled. Well, 2 shells that are filled, but you know, your outermost electrons is in n equal to 3, which is further away. So naturally speaking, your cations are going to be smaller than your atom. Okay, your cations are smaller than your atom. Your anions are bigger than your atom, not because they have 1 extra shell, but because you can imagine looking at number of protons and number of electrons again. So the atom has equal number of protons and electrons, but the electrons in the anion is 1 more because of the single negative charge. Okay, so here you can tell that both are in n equal to 3 shell, because this is just 1 shot of argon electronic configuration. You just add 1 more, so both are still filling the same shell. We don't use the same argument here where you have filling in 2 shells versus 3 shells. Okay, so here the argument really is that your number of proton is the same, so your nuclear charge is the same, but going that way you have more electrons. Okay, so more electrons but same number of proton. So that means you have to distribute the proton charge, the nuclear charge of the proton, with more electrons, and therefore your effective nuclear charge is weaker, and therefore size is bigger. That's why your anions are bigger than your atom. That's why your anions are bigger than your atom. Okay, so there's a jagged line there, because in between you have that transition where somewhere from cation, somewhere from anion, so there's nothing in between there. Okay, so C is the correct answer then, and it cannot be that because of what I said about the cations. You know, across that series we talk about same number of electrons but increasing nuclear charge due to increasing number of protons. So you know, your attraction between the protons and the valence electrons are going to get stronger, so your size is going to decrease from the cations, you know, across the cation, from sodium plus to Mg2 plus to Al3 plus. Yeah, this is the trend for first ionization energy across a period in general. where you have the drop between group 2 and group 13, and then the second drop between group 15 and group 16. Okay, so I spent a bit long on this question, but there's quite a lot of interesting periodicity trend that you can derive from it. Yeah, so I hope you learned something from that. So 2a part 7 is asking for which isotope. So they're asking for isotope of an element in the third period, same number of neutrons as that. Okay, so the number of neutron there is the number of nucleon, which is 32, minus 16, which is the proton number, give you 16 neutron. So all we're doing is 23 nucleon minus the proton, that gives us 12. So A is not the correct answer. 24 minus 12 is 12. Again, that is not correct. I mean, we work out the number of neutrons, which are not the same as the number of neutrons for this sulfur 32. Okay, so 31 minus 15, I can tell because the other three are wrong. There is only one correct option there. Okay, so very quickly, just calculate the number of neutrons there. This next question is asking you on ionization energy, and it's asking you what element is it. Okay, so these are what you call successive ionization energy. You are looking for where there is a biggest jump. Okay, from here to here is roughly, okay, I'm just doing rough maths, it's roughly around 900. This one is roughly around 1000. Okay, I'm not trying to be exact here. I'm working out the difference. So this is around 2000. This difference is around 2000, well, 1000 perhaps, if you consider it's like 6000, you know, to 7000. Here to here, this is the biggest one, definitely. It's around, 7000, 6000. So this one is the biggest jump. So we see a drastic increase in ionization energy from, this is the first, the second, the third, the fourth, the fifth, the sixth, the seventh. So it is the 7th electron to be removed that give you such a big jump. That means the 7th electron to be removed must have come from an inner shell, which is closer to the nucleus. And because it's closer to the nucleus, it's more tightly held to the nucleus, and therefore it's so much harder to remove it. If that 7th electron is from the inner shells, therefore you have 6 outermost electron. We are looking at group 16 element. Okay, and that will be tellurium. Okay, because zirconium is actually group 4. Okay, this is not the group 4. This is not the group 4 you will have seen in O level. This is the group 4 in your periodic table in A level. Okay, so this is known as group 14 in the A level periodic table. Yeah, just be aware of what periodic table you are using. Okay. There's group 16 there, and there's group 17. Okay. 2a part 9. So they're asking for a correct statement. So this isotope there, UNP, I don't even know how to pronounce that. The number of proton is 105. That's the identity of the element. The number of neutron is the nucleon number minus the proton number. So what is that? 62 minus 5 is 57. That's 157 neutron. So there's 157 neutron. The nucleon number is 105. That is wrong. It's 262. Is that? That's the nucleon number. They're asking for correct statement. Yeah. The atom, whatever, is an isotope. So they have the same number of protons, but different number of neutrons. So that's actually a correct statement. But let me just check the rest. They are not 262 neutron. They are 157 neutron. The proton number is not 262. It is 105. Okay, that's the identity of the element. So fairly straightforward then. This next question is actually a two-step kind of question. So earlier we talked about where you need to find the identity of the element. You need to work out where is the biggest jump in the successive ionization energy. Here I hope you can see the biggest jump in the successive ionization energy is there. Compared to the rest, some of them are quite big, but this is the biggest of all. So this means the 6th electron must be removed. This is how you explain in a theory paper, and this is how I hope you are thinking about this when you're dealing with this MCQ question. The 6th electron must be removed from an inner shell, because that's why it's suddenly very, very difficult to remove it. So if you remove the 6th electron from the inner shell, that means you must have 5 outermost shell electrons. Because you only have 5 outermost shell electrons, we are looking at a group 15, okay, or in O level you call this group 5 with the Roman numeral. So if you have 5 valence electrons, when you form a chloride, you can think about PCl3, NCl3, AsCl3, etc., etc. Okay, so they are going to look like that. Very soon in structure and bonding, if you haven't done it, it will talk about shape of molecule, where we know that there's a lone pair left on the group 15 element, because they use 1, 2, 3 to form covalent bond. If you're not happy with that, you can draw whatever you have drawn and learn in O level or GCSE. This line diagram where I display the bond, each of which refer to one covalent bond, and therefore a pair of shared electron, one from phosphorus, one from chlorine. You still have 2 electrons on the group 15 element which are not bonded. Essentially, I've used phosphorus as example, but I say it could be nitrogen or arsenic or any of the group 15 element. So they're going to give you XCl3, okay, so because it's a group 15 element there. All right, so this is the end of these short tutorial videos on these multiple choice questions involving atomic structure. I'll catch you in the next video. Don't forget to subscribe if you haven't. If you think these are useful, do leave a like and share with your friends, your colleagues, your students. Yeah, I'll see you in the next video. Thank you.